Have you ever stopped to think, I mean, really think, about how all this stuff works? Our phones, video calls across the planet, streaming movies?
Right, it all seems so seamless.
Exactly. How does that signal, that data, get there reliably, especially with all the, interference and noise out there?
It's an amazing question, and honestly, the blueprint for pretty much everything digital we rely on today, it comes back to this one incredible paper from 1948.
That's what we're diving into today. Claude Shannon's A Mathematical Theory of Communication. This isn't just some dusty old paper. It is literally the mathematical foundation for the digital age.
It really is. It laid out the absolute limits of communication, but also, kind of surprisingly, what was actually possible.
So our mission today, our deep dive, is to pull out those core ideas from Shannon's work. We'll look at some surprising bits and really try to help you get your head around these fundamental concepts that govern how any message gets sent and received.
Yeah, we want to strip away the really heavy math and just get to those key insights, those aha moments.
Okay, let's get into it. Shannon's theory starts with this really counterintuitive idea about what information even is. It's probably not what you think.
Exactly. For the engineering side of things, just getting a message from A to B, Shannon basically said the meaning, the semantic aspects, they're, quote, irrelevant.
Irrelevant. That sounds radical.
It was. The key thing for him was this. The actual message is one selected from a set of possible messages. It's about the choice, the reduction of uncertainty, not what the chosen message actually means.
So it's about picking one possibility out of many. That decoupling of meaning and data was huge, wasn't it?
Absolutely fundamental. It let us treat messages as just data, which is what allows computers and digital systems to process stuff without needing to understand it.
Okay, so it's about choice. And then he brings in this logarithmic measure for it. Why a logarithm? That feels a bit mathy up front.
Well, yeah, but there are really solid reasons. Shannon gave 3. First, it's just super practical for engineers, things they care about, like time or bandwidth or how many relays you need. They tend to scale linearly with the logarithm of the number of possibilities. So like adding one relay might double your possible states, but it only adds 1 to the log base 2. Makes the math way easier to handle.
Okay, so it simplifies things when systems get bigger?
Precisely.
Hmm.
Second, it just kind of feels right.
Mm-hmm.
Intuitively. Like you'd expect 2 punch cards to hold twice the information of 1, right?
Yeah, that makes sense.
The logarithmic measure captures that linear relationship. It matches our gut feeling about capacity.
And the third reason?
Just mathematical convenience, really.
Yeah.
It makes handling calculations with enormous numbers of possibilities much, much simpler. Cleans everything up.
And that logarithmic measure, specifically log base 2, that's where bits come from, right? Binary digits.
Exactly. A term suggested by J.W. Tukey, apparently. One bit is that fundamental choice between 2 equally likely options. Yes or no, heads or tails, 0 or 1.
So when we talk terabytes, we're really just talking about a massive number of those fundamental choices.
That's the core idea. Now, before getting deeper into quantifying information, Shannon laid out this universal model for any communication system, just 5 basic parts.
Why was that important?
So-
To make it general?
Exactly. He wanted a framework that worked for everything, smoke signals, telegraph, radio, whatever. So first, the information source. That's what creates the message. Could be a person talking, could be text, could be sensor data.
Okay.
Then the transmitter. This takes the message and encodes it, turns it into a signal the channel can handle, sound into electrical waves for a phone, or, letters into dots and dashes.
Right. And the channel is just the pathway.
Yep, the channel is the medium, wires, fiber optic cable, radio waves, even the air itself. It's the pipe.
Got it.
Then on the other end, you've got the receiver. Its job is basically to undo what the transmitter did, decode the signal back into a message,
And finally,
the destination, the person or machine or whatever the message is actually for. And Shannon, in this paper, mostly focused on discrete systems. First, or systems dealing with separate symbols like letters or bits.
okay, so let's imagine the perfect world first. No noise, no interference. What's the absolute maximum amount of information that channel, that pipe can carry? That's channel capacity.
Exactly. For a discrete channel, the capacity C is just the maximum rate info can flow. Shannon used the example of a teletype system. Say it has 32 symbols.
Okay.
Each symbol represents 5 bits of information.
Right.
Because 2 to the power of 5 is 32.
Right.
So if that machine can send n symbols every second, its maximum capacity is 5 times n in bits per second. That's the theoretical speed limit for that specific channel.
But the channel's only half the picture, isn't it? There's also the source spitting out the information. And what Shannon realized about sources, especially language, is pretty amazing.
This is really key. Messages, especially in human languages like English, they're not random, not at all. They have this deep statistical structure.
Like E being common, Q being rare.
Exactly. NTH appearing way more often than, say, XP.
Yeah.
This structure, this predictability, means you can use less channel capacity if you're smart about encoding. It provides inherent savings.
And this structure is also what makes language robust, right? Lets us understand things even if they're not perfect.
Absolutely. It's a built-in error correction in a way. And Shannon showed this brilliantly with his series of approximations to English.
Ah, yes. These are fascinating. Walk us through them.
Okay, so he used a 27-symbol alphabet, 26 letters plus the space, the zero-order one, just random letters, equally likely, total gibberish, XFML, RXKHRJ, FFJUJ, CLPWC, FWKCYJ, nonsense.
Right. Sheer noise.
Then, first order. Still picking letters independently, but now using their actual frequencies in English, so lots of E's, T's, A's.
Okay. Slightly more familiar looking.
Yeah, it looks like OCR, HLI, RGWR, NVOS, EULL, and Benezia. You see more vowels, common letters pop up, but still no real words.
Still doesn't make sense.
No. Now, second order. Here, the probability of a letter depends on the one letter before it. This is where it gets interesting. You start seeing plausible bits. On I and Soutenese are T and Corey St. BS Demi Ekin, like little fragments that could be words.
Okay, starting to look a bit like language now.
Getting closer. Third order depends on the two preceding letters. In no ist latwe cradict forburus grossid. Even longer, recognizable chunks start appearing. It's almost teasing you.
Wow.
Then he did it with words. First order word approximation. Pick words based on frequency, but independently. Representing and speedily isn't good, apt, or come can. Grammatically all over the place.
Right.
But the second order word approximation, using word transition probabilities. That's where you get sentences that sound eerily plausible. The head and in frontal attack on an English writer that the character of this point is therefore another method.
That is striking. That phrase, attack on an English writer, that the character of this, it sounds like it could be real. It really drives home how much structure is baked into language.
It's a fantastic demonstration. All that predictability is just sitting there.
So this statistical nature, this predictability, it leads directly to another massive contribution, right? A way to actually measure this uncertainty or choice.
Exactly. This is where entropy comes in, usually written as H. Shannon needed a mathematical way to quantify this uncertainty for a set of possible events, each with its own probability.
And he had some rules for what this measure should do.
Yeah, three key intuitive properties. One, continuity. Small changes in probability shouldn't cause huge jumps in H. Makes sense.
Okay.
Two, monotonicity. If all your options are equally likely, having more options should mean more uncertainty, so H should go up.
Also makes sense. More choices, more unpredictable.
Right. And three, the decomposition rule. This is clever. If you can break a choice down into a sequence of smaller choices, the total entropy is just the weighted sum of the entropies of those smaller steps.
Okay. Like figuring out the total uncertainty of a complex lottery by looking at the uncertainty at each stage?
Pretty much, yeah.
Yeah.
It's additive in a specific weighted way. And the big question then was, is there only one mathematical function that actually behaves like this?
And the answer?
Amazingly, yes. Theorem 2 in the paper proves it. The only function that satisfies those three reasonable assumptions is hk times the sum of pi log pi for all possibilities.
Right.
K is just a scaling constant, usually 1 when we measure in bits.
Wow. So that famous formula wasn't just pulled out of thin air. It was derived from basic assumptions about how uncertainty should behave.
Precisely. It's deeply fundamental.
So what does this number H, this entropy, actually tell us?
Well, a few key things. H is 0 only if there's no uncertainty if the outcome is guaranteed. Otherwise, it's always positive.
Right. No choice, no information needed.
Also, H is biggest when all outcomes are equally likely. That's peak uncertainty. Maximum surprise, you could say.
Okay.
And here's a cool one. The uncertainty of two things happening together, HXY, is less than or equal to the sum of their individual uncertainties, HX plus HY.
Less than or equal? Why
Yeah.
not just equal?
Because X and Y might be related. If knowing X tells you something about Y, then knowing both gives you less total new surprise than knowing them separately would suggest. They only add up perfectly if X and Y are totally independent.
Ah, I see. So knowing something about one event reduces your uncertainty about another related event.
Exactly. Knowing Y is never increased by knowing X. Usually it's decreased. That's why knowing a message is English helps predict the next letter. The letters aren't independent.
Okay, so With entropy defined as this measure of uncertainty, Shannon could then look at language again and quantify its inefficiency. Is that the right word?
Yeah, or waste, though maybe predictability is fair. He called it redundancy. First, you defined relative entropy, how much entropy a source actually has compared to the maximum possible entropy it could have with the same symbols if they were all equally likely and independent.
Okay, like a percentage of the maximum possible uncertainty.
Exactly. And redundancy is just 1 minus that relative entropy. It's the fraction of the message that's kind of fixed by the rules of the language, not freely chosen by the sender.
And the punchline. What did he find for English?
Get this. He estimated the redundancy of written English is roughly 50%.
50%. So half of what we write is sort of predetermined by the language itself.
In a statistical sense, yes. About half is choice, half is structure. It sounds wild, but it explains why we can often guess missing words or letters or understand speech in a noisy room.
How did he figure that out?
Well, partly from those language approximation experiments calculating their entropy. Also, by experiments where people had to guess letters in a text. If you can correctly guess, say, half the letters without seeing them, the redundancy must be at least 50%. Cryptography techniques also pointed to a similar figure.
That 50% redundancy, it has some fun side effects too, doesn't it? Like with crossword puzzles.
Ah, yes, the crossword puzzle example is brilliant. Think about it. If English had zero redundancy, any random string of letters would be valid. Crosswords would be impossible because there'd be no constraints. Any letter could go anywhere.
Total chaos.
Right. But if redundancy was, say, 90%, the language would be so restrictive you couldn't find enough words to fit together in a complex grid. It would be too rigid.
So 50% is like the sweet spot.
Shannon argued, based on a sort of statistical analysis, that large, complex crossword puzzles are just possible around that 50% mark. He even joked that if redundancy were lower, maybe 33%, you might be able to make three-dimensional crosswords.
That's fantastic. It's amazing how this abstract math suddenly connects to something so everyday. Really shows the power of the theory. Okay, so we've talked about ideal channels and the structure of language, but the real world isn't ideal. It's noisy. Signals get messed up. What happens then?
Right. Noise is the big enemy. And Shannon was clear, this isn't just simple distortion, like a signal getting weaker but keeping its shape. Noise is random. It adds unpredictable changes, making perfect reconstruction at the other end impossible.
Impossible. So errors are inevitable.
Well, the raw signal will have errors. But here's where people often make a mistake. Let's say you're sending symbols, and maybe 1% of them arrive wrong because of noise. Does that mean you've automatically lost 1% of your information?
It sounds like it should, right? Send 1,000 bits, 1% error, you get 990 bits of info through.
Seems logical. But Shannon showed that's wrong. He used an extreme example.
Wait.
What if the noise is so bad that the received symbol has no statistical connection to the sent symbol, like the receiver's just flipping a coin for each bit?
Yeah, okay.
Well, just by chance, about half the received bits would match the sent bits. But are you transmitting any information?
No, of course not. It's just random luck.
Exactly. Even with 50% correct bits, you're transmitting zero information. So just counting errors isn't the right way to measure information loss due to noise.
So we need something else, a way to measure the actual uncertainty introduced by the noise?
Precisely. And Shannon introduced the perfect concept, equivocation, usually written high X. Think of it as the remaining uncertainty about what was sent X, given that you received a particular noisy signal Y.
So it's the ambiguity, how much you're still unsure about even after getting the message.
That's a great way to put it. It's the information that's gone missing, scrambled by the noise. So back to that 1,000 symbols per second, 1% error rate example.
Yeah.
Shannon calculated the equivocation for that specific case. It works out to about 0.081 bits per symbol,
Okay.
which means over 1,000 symbols, you're losing 81 bits per second to ambiguity caused by the noise. So the actual rate of information getting through isn't 1,000, and it isn't 9990. It's 1,000 minus the equivocation 81, so 919 bits per second.
Ah, that makes much more sense. It directly subtracts the uncertainty caused by the noise.
Exactly. And in that coin flipping case, the equivocation is 1 bit per symbol, so the rate is hx1, which is 0 if the input was random bits. Perfect. Theorem 10 basically says this equivocation is exactly how much extra info you'd need to magically get at the receiving end to perfectly correct the errors.
Okay, so with equivocation, we can properly measure the net information rate. How does this redefine channel capacity for a noisy channel?
The capacity C of a noisy channel is the maximum possible rate you can get, after accounting for equivocation. You find it by trying all possible ways of sending signals, all
Okay.
possible input statistics, and finding the one that maximizes HX, HX. That maximum value is the true capacity of that noided channel.
It's the absolute best you can do reliably over that specific channel.
That's it.
Which brings us, I think, to maybe the most stunning result in the whole paper, the fundamental theorem for a discrete channel with noise.
Theorem 11. Yes, this one really turned communication theory on its head. It's profound.
Lay it on us.
Okay, it has two parts. Part one, if the rate you're trying to send information at, let's call it R, which is related to the source entropy H, if R is less than or equal to the channel capacity C,
So if you're sending slower than the channel's limit.
then it is possible, theoretically possible, to invent an encoding scheme that lets you transmit that information over the noisy channel with an arbitrarily small probability of error.
Wait, arbitrarily small? You mean essentially error-free, even with noise?
Essentially error-free. As close to zero errors as you want to get, provided you're below capacity.
That is mind-blowing. How it sounds like magic. Noise is still messing things up, isn't it?
It is, but the magic isn't in stopping the noise. It's in clever coding. Specifically, adding redundancy in a very structured way. This is different from the redundancy in the language itself. This is coding redundancy you add on purpose.
Like error-correcting codes, checksums and things.
Exactly like that. But Shannon proved their theoretical power before many practical codes existed. He used an example. Imagine encoding blocks of, say, 4 message symbols into a block of 7 transmitted symbols. Those extra 3 symbols aren't carrying new information. They're carefully calculated based on the first 4.
Okay.
They're designed so that if, say, only one of the 7 symbols gets corrupted by noise, the receiver can figure out which one it was and fix it.
So the redundancy lets you pinpoint and correct errors.
Right. In that specific 7-symbol example, you can correct any single error perfectly, achieving reliable communication at a rate of 47ths of a bit per symbol. Now, to get arbitrarily close to capacity C with arbitrarily few errors, you generally need to use very long blocks of symbols.
So there's a trade-off. You need delay to process these big blocks.
Yes, there's typically a delay involved. You have to wait for a large chunk of data to come in to do the sophisticated encoding and decoding needed to get close to that theoretical limit.
Okay, so error-free is possible below capacity. What's the second part of the theorem? If you try to go faster than C,
Then you're out of luck. If your source rate R is greater than the channel capacity C, it is impossible to transmit the information without errors. There will always be a minimum amount of equivocation of uncertainty equal to at least the difference, R minus C. Shannon said, nature takes payment by requiring just that much uncertainty. You just can't cheat the capacity limit.
wow. So C is a hard wall. Below it, perfection is possible. Above it, errors are guaranteed. That's incredible. And he proved this exists without necessarily showing the exact codes.
That's the genius of it. He proved the possibility based on probability and averages over long codes, paving the way for decades of work by others to actually find practical codes that approach this limit.
Amazing. Okay, so far, mostly discrete stuff, letters, bits. But what about continuous signals? Things like sound waves, radio, video.
Right, the analog world. Shannon tackled that too. He built on work by others like Nyquist and Hartley, particularly the sampling theorem.
Which says you can represent a continuous signal with discrete samples.
Exactly, if you sample fast enough. So you can bridge the gap between continuous and discrete. Now, calculating entropy for continuous signals gets a bit weird. The value can depend on the units you use. It can even be negative.
That sounds confusing.
It is a bit subtle, but the key thing Shannon showed is that what matters, the rates of information and the channel capacities, these always come out non-negative and independent of the coordinate system. Differences in entropy are what count, and those are well behaved.
Okay, so the core concepts still apply, and this leads us to maybe the single most famous equation associated with Shannon.
I think you mean the Shannon-Hartley theorem, Theorem 17 in the paper. It gives the capacity for a very common type of continuous channel, one limited by bandwidth and affected by white Gaussian noise.
That's the one. What is it?
It's beautifully simple. C, W log 1 plus Pn, bits per second.
Okay, let's break that down. C is capacity, the maximum rate.
Yep, the ultimate speed limit in bits per second. W is the bandwidth of the channel in hertz. Think of it as the width of the pipe available to you.
B.
P is the average power of the signal you're transmitting, how loud you're shouting, basically. N is the average power of the noise, specifically that background white thermal noise that's unavoidable in electronics. P over N, Pn, is the crucial signal-to-noise ratio, SNR.
So the capacity depends on how wide the pipe is, W, and how strong the signal is compared to the background noise. Again.
Precisely. More bandwidth gives you more capacity. A better signal-to-noise ratio also gives you more capacity, but logarithmically so, doubling your power doesn't double your capacity.
And this is the absolute maximum.
According to the theorem, yes.
Yeah.
For that channel model, you cannot, physically cannot, send information reliably faster than C bits per second over that channel, no matter how clever your modulation or coding scheme is. Try to go faster, and errors are guaranteed.
That equation dictates so much of modern technology, Wi-Fi speeds, 4G, 5G limits.
Everything. It tells engineers the fundamental trade-offs between bandwidth, power, and data rate.
Mm-hmm.
And interestingly, to actually reach that capacity limit, the theory suggests your transmitted signal should statistically look a lot like white noise itself.
Huh. Fight noise with noise-like signals. Okay. Now, for these continuous sources like music or video, you said perfect transmission is impossible, right? Infinite bits needed.
Theoretically, yes, to capture every infinitesimal detail. So in the real world, we don't aim for perfection. We aim for good enough. We care about fidelity.
Meaning, how close is the received version to the original?
Exactly. Transmitting it to within a certain tolerance, we accept some loss, some compression, as long as the result meets a certain quality standard. Like, is the audio clear enough? Is the video sharp enough?
And Shannon found a way to quantify this good enough.
He showed that any reasonable way of judging fidelity could usually be boiled down to calculating some kind of average distance between the original signal and the recovered one.
Distance.
Yeah, like a mathematical measure of difference. A common one is the RMS criterion root mean square error. It's basically like measuring the average power of the different signal, the error signal.
Okay, so you define how much error you're willing to tolerate.
Right. Or you could use fancier measures, like ones weighted by frequency, or even conceptually something based on human perception, like speech intelligibility scores.
And this leads to another rate definition.
Yes, the rate R1 for a source relative to a specific fidelity level V1. This R1 is the minimum number of bits per second you need to transmit to reproduce that source with at least that level of fidelity, V1.
So it's the minimum data rate needed for a certain quality, like the byte rate for an MP3 or a video stream.
Exactly like that. It connects the source's inherent complexity at a given quality to a required data rate.
And then there's a final theorem tying this back to the channel capacity.
Yep, Theorem 21. It's beautifully simple, really. It says, if a source has a rate R1 for fidelity V1, you can transmit it over a channel with capacity C and achieve that fidelity, if and only if R1 is less than or equal to C.
So the channel's capacity must be at least as large as the minimum rate required by the source for the quality you want.
That's it. If R1's C, you simply cannot achieve that fidelity level over that channel. The pipe isn't big enough for the quality you're demanding. For simple cases like sending a noisy signal and wanting a certain RMS error, he even gives a formula for R1. R was W1 log Qn, where W1 is the source bandwidth, Q is its power, and N is the allowed error power.
It brings everything together, the source, the desired quality, the channel limits.
It really does. So,
Stepping back, what an incredible journey Shannon took us on in this one paper. He quantified information itself, defined the absolute limits of communication, noise or no noise, discrete or continuous. It's just staggering.
it truly is. The key takeaways are immense. Information is selection, measured in bits. That universal five-part model of communication, the power of statistics and redundancy in language.
Entropy as the measure of uncertainty, equivocation as the measure of information lost to noise.
The mind-bending idea that error-free communication is possible below channel capacity. The Shannon-Hartley law is setting that ultimate speed limit based on bandwidth and SNR.
And finally, connecting source complexity and desired fidelity back to that channel capacity. It covers so much ground.
It's a theory about the very fabric of communication, completely independent of what is being communicated or the specific technology used. That's why it's still so relevant.
It is. And, thinking about how Shannon deliberately separated the meaning from the engineering problem of transmission, that was necessary. It enabled everything we have now.
Absolutely.
But it makes you wonder, how has that deliberate decoupling shaped the digital world, this vast, efficient, but sometimes impersonal flow of data? What happens is we keep building systems focused purely on efficient transmission, maybe sometimes at the expense of, shared understanding or context.
That's a really profound question to ponder. The efficiency is incredible, but does something get lost when meaning is officially irrelevant to the system?
Definitely food for thought. Hopefully, this deep dive gives everyone listening a new appreciation for the hidden mathematical beauty behind every email, every stream, every call. It's quite
Yeah,
something.
it really is. Shannon gave us the language to even talk about these limits and possibilities.